Hey, what's up? Patrol Pal, Mr. Cook. So we got through the first two parts of number one. We graphed it. Now I'd like to, I kept the graph up here, complete with that point I got from 2B, was it 2.507, I think. And now it's asking us to find the total distance. Now, when asking you to find total distance, what that means, if it's like a pretty simple integral, usually, like if you wanted to find like the change in position, you'd do this. So change in position. You take the integral of the velocity function over some period of time. Oops, dt, sorry. So like from 0 to 3. But if it says find the total distance, what changes is that you got to take the absolute value of the velocity function. Okay, so this makes it now a total distance traveled. And again, if you have your calculator, this is like super easy. You quite literally just need to plug in everything, on there. So if I have my calculator, here's how I'd write it up. Integral from 0 to 3, and I'd use absolute value and then type in the velocity function. So that's going to be negative t plus 1, then times the sine of 1/2 t squared, and then dt. Just type that in. But if you have to kind of do this by hand, you'd want to split it where it goes here, because here's where you'd have like a negative velocity and a positive velocity. So you'd want to make sure that you account for that. Okay. So last little thing is just type it in and get your answer. It'll be some units rounded to 3 decimal places, and you're not really going to need units on it because they didn't give us units for anything. So let's type it in. Oops. And by the way, if this was a in the context of like our final exam, we would give you a really easy function, take the antiderivative, if you have to do it by hand, or we'd just ask you to leave it in terms of like set up the integral but don't solve it, like one of those kind of problems. Anyways, so let's see, math, integral FNINT, there we go. Okay, we're going from 0 to 3. And then absolute value, I think that's in math. Yeah, number, there we go, absolute value. And then negative parentheses x plus 1. And then times the sine of 1/2 of x squared. There we go. Now absolute value ends. Dx. Okay, and then we should get, let's see here, number, what we get? Come on, you can do it. 4.334-ish. And there's our, our area under the curve, or the total distance that's been traveled. That's about it. And, again, if you're doing this by hand, then you'd want to split this into two separate integrals. So like you'd have the negative one first. So you go from 0 to, or that point where the graph turns around, square root of 2 pi or whatever it is, and then your function, so v of t, whatever it is. But here's the thing: this is going to give you a negative area, but you need to turn it positive because of the absolute values. So what you do is you just put a negative in front, because if it's a negative times a negative, it turns it positive. And then plus, and then you add on the other integral. So starting at 2.507, or square root of 2 pi, going over to 3, and then same thing, the velocity function. But this time, the area is going to be positive. So you can just leave it as is. You can just leave that little plus sign on there. And it would still give you like that number for your answer. Okay, so that's number 1C. This whole problem, number 1, is just going to take a long time because of the subject matter. It's a physics problem. If this was just like graphing or interpreting a graph, it'd be a lot easier, but you have to do computations, and that makes it a little more challenging. But again, the main things that you want to pick up from this, the position function, if you take the derivative, it gives you the velocity. If you take the velocity function and you take its derivative, it gives you the acceleration. Those kind of things. And like Speed is increasing when the velocity and acceleration have the same sign. Either they're both negative or both positive. What else do we do? If you see the distance traveled, that's going to be equal to integral of some boundary, and then the velocity function, its absolute value. Just, stuff like that. Those are the things that you want to remember, not necessarily all the little odds and ends that we did on this. Okay, 2. So with number 2, we're going to, it looks like we got a table. Usually, and this is true for the AP test as well. They usually have graphs or they have tables. So just kind of be aware of that, but don't be intimidated. Tables are pretty easy to work with because it's just usually, it's values that you imagine that you don't have to plug them into calculators and stuff. And same thing with the graphs. If they give you graphs, it's because, all the information that you need is going to be on the graphs or on the tables. That's kind of what I'm trying to say. Anyways, the rate of fuel consumption in gallons per minute recorded during an airplane flight, is given by a twice differentiable and strictly increasing function, R of time t. The graph of R and a table of selected values of R of t for the time interval from 0 to 90 minutes are shown. Okay, so here's our interval, our timetable, and then our graph. And remember that this is R of t, okay? It's in terms of gallons per minute. Part A says use data from the table to find an approximation for R prime of t. Well, R prime of t means find the derivative of 45, right? Of R at the time 45. Show the computations that lead to your answer and indicate the units of measure. So here's how I do it. Well, an approximation for R prime of t, if you just remember that R prime is the derivative, right? T, I'm sorry, is the derivative. And just remember that a derivative is the same thing as, the slope of the tangent line at some x, same thing here, derivative at some time t. So let's change that to t. And, the derivative is the slope of the tangent line, and it's also the same thing as the instantaneous rate of change. At some time t, okay? So if they're asking for an approximation of the derivative, I can just approximate any of these things, approximate the slope. So that's what I'm going to do. I'm going to approximate the slope. Even though I don't have an exact point right here where I can find the derivative and get it, check it out. If I use points around it, I'm going to get a slope, and it's going to be pretty close to what that's going to be, right? As long as it's continuous, mean value theorem says that there's some value in that interval where the derivative should be equal to that slope, that secant slope of the average rate of change. So that's what we're going to do. So here's how we write up our justification and all that stuff, or showing the calculations. We'd say that R prime of 45, or in other words, the derivative of R at 45, is about equal to the average rate of change. Over some interval. And the interval that we're going to use is where 45 is around, So 40 and 50 would be the numbers that we're going to use. So that's what we're going to say. We're going to say that R prime of 45 is going to be equal to, about equal to, it's approximate. It's going to be F of 50, so I'm just using average rate of change formula, minus F of 40 all over 50 minus 40. That's, the slope formula, if you will. It's just repurposed for all functions, okay? And that approximation is about equal to what? Well, F of 50 is 55. F of 40 is 40 also. So 55 minus 40 is 15. 50 minus 40 is 10. And then 10 and 15 are both divisible by 5. So that turns into 3 halves. And then you'd want to put the units on there, of course. And here's how you do it. So if it's the derivative of R, the time derivative of R, so we're doing dr dt, right? Well, R of t is gallons per minute, right? That's R of t. and then T is minutes. So that means that it's going to be gallons per minute per minute. In other words, gallons per minute squared. There's the units on it. So that's part A. This should be pretty easy. Okay, now let's move on to part B. All right, so part B says the rate of fuel consumption is increasing fastest at time t equals 45. What is the value of R double prime of 45? Explain your reasoning. So when it says increasing the fastest, that's like just word association. You should know that if it's increasing the fastest or decreasing the fastest, that's going to happen at the inflection point. Okay, so that's what I would say. So I'd say something like this for this problem: increasing fastest at the inflection point. And then it says what is, well, the rate of consumption is happening in 45 minutes. So that means that R, so I'd say therefore R double prime of 45 is going to be equal to 0. Now here's why I would say it's equal to 0. Then I'm going to put units in a second. It's because the inflection point happens when you take the second derivative, of a function, and you either set it equal to 0, and that can find a critical number for the second derivative, or you see where it gives you a DNE kind of situation, because that can happen as well. And I can exclude the DNE situation because it says it's twice differentiable and strictly increasing, so it's not like a DNE kind of thing. It doesn't say anything about that. No domain restrictions. So I'm to assume that it's just going to be equal to 0 at that point. Now for the units. So remember before R, dr dt gave us gallons per minute, right? Well, we're going to take the time derivative again. So we're going to divide by another minute. So that means that ultimately we're going to get gallons per minute cubed for this one. And I'm not sure if they're really adamant about getting the units on that, but you probably should just include it just in case. All right. Then the next thing, so let's see here. Approximate the value of the integral from 0 to 90 of R of t using a left Riemann sum with 5 subintervals indicated by the data in the table. Excuse me. I'm gonna grab some water real quick. Hold on a second. Okay. So this leads me to another kind of thing, word association that I wanted to bring up. When you see this, expression, some integral of a function over some bound. This is what we call, the definite integral, of the function f of x over some interval. Okay, so from A to B. So this this symbols, that's what it means, definite integral of f of x over A to B. And what this means also, another way that you could see it described is as the area under the curve, of the function f of x with respect to the x-axis in this case. That's how you might see it phrased. Maybe it just says area on the curve, but you get the idea. It's the same thing as definite integral. And from the fundamental theorem of calculus, this also means that you take the antiderivative of the function f and just plug in b and plug in a and then subtract it. Right? That's the other thing. So here's the word association that you should know for these. And this is going to help us out actually in this problem. And I think maybe 3. Yeah, also 3. So those are pretty helpful to know. All right, so C, it's helpful because if I'm trying to approximate it, I can just approximate the area under the curve. That's what I'm going to do. And I'm going to use something called a left Riemann sum to do that. So in a left Riemann sum, you divide up your intervals. So I have 5 intervals from these tables right here. I have an interval from 0 to 30, So that's like this part here, that interval. And then I've got another interval that goes from 30 to 40. So that's like this interval here. And then I've got another interval from 40 to 50. So that's going to be this interval here. I've got, two more intervals. There's another interval. Let's pick a nice color. Let's see here. How about purple? Yeah, that's good. Another one from 50 to 70. That's this one here. And let's, do one more color. Let's do orange. Feeling in a sun's mood today, I think. And then we have one more interval from 70 to 90. So that's this one right here. So in a Lefferts-Munson, what you do for each of these intervals, you're going to create a rectangle. And in each rectangle, you have the base for one of the rectangles, like this orange one, for example. This base is going to be a difference from 70 to 90, so a length of 20. And then to make the height on the rectangle, because it's a Lefferts-Munson, we're going to use the left endpoint. So the leftmost endpoint is here at 70. So I'm going to go over to the coordinate for 70, that one, and make a little rectangle for it. It's going to look something like this. So there's my, fifth interval right here, and it has dimensions of 20, and then this height is going to go up to the, that point where 70 is, so 65. So 65 is going to be the other dimension for it. And similarly, I can set up the other intervals. I got to get my purple color back. There we go. So next interval from 50 to 70, so that's this one here, right? Well, the base is going to be a length of 20 again, and the height is going to be determined by the left endpoint. So this one over here at 50. At 50, it's going to be 55. So the height goes all the way up to that point, 55, and then it goes out over here. This is my fourth subinterval, and this height over here is going to be 55 with a base of 20. So I can just multiply those together to get my area. The next interval is going to be the red one. So it's going to go from 30 to 40. So the leftmost endpoint here. Oops, I skipped the green one. Darn it. Sorry. So it's my green one here going from 40 to 50, and the leftmost endpoint is at 40. So at 40, it's going to be a height of 40. So all the way up to the point right there. This is my third interval. It has a height of 40. And then my next interval is going to go from 30 to 40. So the leftmost point is going to be 30. So the height at 30 is going to be 30. For that one, for this second rectangle, second interval. I forgot to put the bases on there. There we go, 10 and 10 for each of them. And then the last one is my first interval. And the leftmost value is 0. And so that's going to be a height of 20. It looks like a base of 30. Okay, so to approximate this using a Lefferts-Munson, what I'm going to do is write it up like this. R of t, the integral going from 0 to 90, dt is going to be equal to, and then I'm going to add up every one of those little interval areas, okay? And also I should use approximately equal to, because it says that magic word approximate. Okay, so the first rectangle is here, and the base is 30, the height is 20. And then the second interval is here, the base is 10, the height is 30. And then I have the third interval, and the base is 10, the height is 40. And then I've got my fourth interval here, base of 20, height of 55. And then my last one is the fifth interval. It has a base of 20 and a height of 65. So I add all that stuff together, and that'll give me my approximation for the Riemann sum. So I use my calculator for that one. So let's see here, 30 times 20 plus 10 times 30. I can probably do some of this in my head. Plus 40 times 10 is 400. Plus 20 times 55 is 110. Wait, that'd be times 2, so 1,100. And then 20 times 65, so that's 13, so I think it's 1,300. And if I add them all up, I get 3,700. So it's going to be 3,700, and then I need to have the units on it. Now, Remember how we did the derivative? We can do the same thing here. If we just count up the units, so R of T is going to be gallons per minute. Now we're multiplying by dt, so we're going to multiply by minutes. Notice that the minutes cancel out, leaving us just with gallons. All right, and then part D says, using your approximation in part C, how much tank fuel or total fuel was consumed during the entire 90-minute flight? This is a trick question because it just seems like that's just the same thing as the answer from C. So, yeah, I think that's right. Yeah. It's got to be. Wow. Okay. Well, how much fuel was consumed during the entire 90-minute flight? Yeah. That's just what it would be. It'd be like, the same thing. R of T dt, which we know is about 3,700 gallons. So I think that's all it's asking to find. Gallons consumed, maybe. That's interesting. I've never seen a problem where it just asks the same thing back to back, but whatever. All right, there's C and D. All right, well, that's it for this video. Thought I'd finish up number 1 and then do all of number 2 because it's pretty quick. All right, I hope you found this helpful. If not, go talk to your calc teacher. I'm Mr. Cook. If you want some help, you can always find me. I'm usually available before school or after school. So just hunt me down and, we can work on the calc stuff. You can ask any questions. Okay, I hope you found this video helpful, and I'll see you in the next one. Bye-bye.